In this video, we're going to go through a worked example to find the point on one function that is parallel to another function. So let's jump in. Okay, so this is the problem we'll be working on throughout this video. And by the way, this is a calculator problem, so feel free to use one for this problem. But either way, go ahead, pause the video, and see what you get as an answer. Okay, so here's the answer. If you were able to find these points easily, then go ahead and skip to the next video. Otherwise, we'll dive into exactly how we got this. First, let's think about what they're even asking. Here's a quick visualization I built on Desmos. Basically, we have two functions. One is y equals secant of x, and the other is 3y minus 2x equals 4. And basically what they're asking us to find is the point on secant x. If I turn on the tangent line, they're asking us to find the point on secant of x that is parallel to this other line, where the tangent line is parallel to that other line, I should specify. So apparently, it looks like at around 0.54, that seems to be an answer. Again, not exactly. We'll figure out exactly what it is sooner, or later. But it looks like it's about 0.5-ish. And then this goes a higher slope. And then if we pull this down, now we kind of pop out down here, and it looks like somewhere around here. Again, I don't know where the exact value is, but 2.62-ish. That seems to also have the same slope for the tangent line to secant and this line right here. And then as we keep going, it doesn't seem like we run into that again, at least between 0 and 2 pi. Remember, they're only asking between 0 and 2 pi. So that's kind of conceptually what we're trying to do. Now the question is, how do we do that? So in order to solve this, let's think about what parallel even means. Now, if you remember from algebra, two lines are parallel if they have the same slope. One of these lines is actually a straight line. The other one is a curve. But for the straight line, we can actually figure out what the slope is without using calculus at all. If we just algebraically manipulate this so that it is in slope-intercept form, hopefully it makes sense that this would be y equals 2/3 x plus 4/3. So we basically add 2x to both sides and divide by 3. Now this is in slope-intercept form, and we can tell that the slope is 2/3. So if that's the slope of this line, when would this curve be parallel to that line? Basically, whenever the tangent line to this curve equals this slope. So effectively, and remember, what is the way that we can figure out the equation of the slope of the tangent line? Or just the slope of the tangent line, I should say? Basically by taking the derivative. So all we really need to do here is set this derivative, secant of x, equal to 2/3. Now, how do we take the derivative of secant of x? This is something you'd have to remember from your trig derivatives. But if you remember your trig derivatives, you can recognize that it's secant of x, tangent of x. So there you go. Any x value that makes secant of x, tangent of x equal to 2/3 will be the x values where the slope of the curve is actually the same as the slope of the straight line. Now, how do we actually find this point? Here, it's actually kind of difficult to solve it by hand, or it's actually too difficult that you don't want to go that route. It's better to use a calculator. So basically, you can plug this into a calculator as one function, and you can plug y equals 2/3 into the calculator as another function, and just see what their intersection points are. So let's go do that. So here you can see that I've graphed y equals secant x tangent x, and I've graphed y equals 2/3, and basically we're looking for the x values that make them the same. And here they are. So apparently, what we just found is when x is equal to pi over 6 and 5 pi over 6, that seems to work. Now, honestly, on Desmos, it's pretty easy. You just type in the equations, and Desmos straight up tells you what the intersection point is, or the intersection points. There's two in this case. If you have a TI-84, it's a little bit more complicated. So here we found that the correct x values are pi over 6 and 5 pi over 6. But remember, that's not what the problem asked for. The problem asked for the exact points, which would include the x and the y coordinates. So here, you don't actually need a calculator to do this. You're expected to be able to evaluate this on your own. But one thing that's useful to be able to do is to plug these in and see what you get. So if you plug these in, apparently you get 1.1547 on your calculator. Again, another way you can think about it is if you already know that cosine of x, if you're already familiar with your unit circle, in other words, you could say that cosine of x is basically at these values. So cosine of pi over 6, for example, again, if you're comfortable with the unit circle, hopefully it makes sense that that's radical 3 over 2. And because secant is the reciprocal of cosine, hopefully that makes sense that this first value will be basically 2 over radical 3, if you want to leave it like that. That's why we have, actually I should specify this, if I do f of pi over 6, you can see that that's the same value. And then for the other one, f of 5 pi over 6, again, you can think about this. This is essentially the same reference angle, but it's in the second quadrant where cosine is negative. So you can see here that we get basically just the negative of what we had before. And you can see that these are the same. So again, you could find this by hand on your own, for this portion of the problem, but it's actually easier to work it out like we have here. So there you go. Hopefully that makes sense. Apparently at these points, pi comma 6, or pi over 6 comma 2 over radical 3, and again, you could rationalize this denominator to be 2 radical 3 over 3 if you wanted. And then at the negative of that, basically, those apparently are the points where the slope of the tangent line to secant of x equals the same slope as the other curve. And if we go back to these points on the original curve, so like pi over 6, for example, yep, that is believable that pi over 6 is the exact point where the two lines are parallel. And then remember the other one was 5 pi over 6, or 5 pi over 6. Yep, that's believable. So yeah, I would say overall these points are absolutely believable. One other quick point I would like to make before we go is that you technically didn't need a calculator to solve this. It's just that it would help a lot. How could you solve this without a calculator? You would have to get very clever here. Basically, what you would have to realize, you'd have to solve this expression. Again, in this format, it's not really obvious what it is. But if you think about the different values on the unit circle that we can have for, say, sine and cosine. So like sine and cosine can have, if you think about the general values that we remember on the unit circle for those, it's basically 0, radical 3, or I'll say 0, 1 over 2, radical 2 over 2, radical 3 over 2, and 1 at different values. For tangent, it's actually a little bit different. It's basically 0, radical 3, I'll say here, 1 over radical 3 is better. 1 over radical 3, 1, right, at 45 degrees. Basically, that would be a slope of 1. And then you could also have radical 3 at 60 degrees. And then this is kind of infinity. So if you are very comfortable with your unit circle and you notice a clever pattern here, you could actually solve this without a calculator. How could you do it? Basically, the trick is we want to somehow involve these. So if these are sine and cosine, right, basically the reciprocal of these would be secant and cosecant, but I'll just focus on, I'll say cosecant and secant. And again, these are really just the specific values on the unit circle that we tend to remember. So like at 0, that would be infinity, hopefully it makes sense. And then here, that would be 2. Here would be, hopefully it makes sense, radical 2. Because if I do 2 divided by radical 2 and I rationalize that denominator, I would just get radical 2. This one is 2 over radical 3, and then this one's just 1. So these are typically the values that we remember for secant and cosecant. And now here's where things become interesting. Is there any way, because again, we're talking about secant and tangent, is there any way we could kind of mix and match two of these to make them 2/3? Well, the only thing I only see two options that have 2 in a numerator here, and that's these two. So, and then here, this is actually kind of an interesting pattern, because if you see here that you have radical 3 right here, the question is, what values also have radical 3? So here, there's a radical 3 here, and there's also a radical 3 here. The trick in this case, I'll say, is actually if you cleverly mix and match these, you could solve this problem without a calculator. Because remember, the answer was actually pi over 6 and 5 pi over 6. Those are like actual angles that we remember on the unit circle. So we should be able to solve it actually without a calculator, even though it's a lot more difficult. So here, I guess what I'm getting at is that if you rearrange this thing, let me put it this way, if you rearrange this thing as 2 divided by radical 3 times radical 3 over 3, then you could figure this out. And now again, just to point out, radical 3 over 3, if you rationalize the numerator, that would actually equal this thing. Hopefully that's clear. So that's really the same thing. So basically the question we're asking, is there an x value where secant is equal to 2 over radical 3 and tangent is equal to radical 3 over 3? That's the question. And actually the answer is yes. Because secant is equal to 2 over radical 3 when what? Basically when cosine is equal to radical 3 over 2, and that happens at pi over 6, right? And then tangent, when is that equal to 1 over radical 3? That's also pi over 6. So that makes sense. That's why pi over 6 is an answer, because that's the x value that would cause both of these to equal this. So again, this is hopefully you can see this is way more complicated, but if you're very clever and you're kind of a master with the unit circle, you could do it without a calculator. Now the other thing here is where is secant? There are other values. If you think about it, this number needs to be a positive number. Cosine is positive in quadrant 1 and 4. Tangent is positive in quadrant 1 and 3. So we actually, if basically only one of these is a positive value, like, well, let me back up actually. If they're both positive, like they are in quadrant 1, then this number will be positive. So check, we found that. Pi over 6 is the value in the first quadrant that would make that happen. In the fourth quadrant, cosine would be positive, but tangent would be negative. So positive times a negative would be a negative, so that's not what we want. So in terms of the quadrants, 1 we already took into account. 4 we would have basically cosine or secant positive but tangent negative, so we don't want that. And then with quadrant 2 and 3, think about this. So in quadrant 2, cosine would be negative and secant would therefore be negative, but so would tangent. Tangent would also be negative. And a negative times a negative is a positive, and we know we have a positive number here, so that actually works. So basically we could use that information to figure out that we want this angle also in the second quadrant. That's how we could get to 5 pi over 6, I guess is what I'm getting at, which was the other answer, if you remember. So you could solve this. Again, the trig stuff here is kind of a separate issue, but yeah, technically you could have solved this without a calculator. It would have just been a lot more complicated and you have to be a lot more clever. Realistically, you should use a calculator for something like this. I consider this kind of overkill to do by hand, but you can do it. It is possible. So there you go. That's just one thing I wanted to add to the end of this, but hopefully this has nothing to do with kind of the original problem. All the logic that we talked about is still true. So there you go. Hopefully all that makes sense. If you have any questions, feel free to leave any comments in the comment section. And other than that, I will catch you next time. See you.